Hello guys, in this video we are going to study some measurement of inductance by Maxwell inductance bridge. The topic that I'm going to cover in this video is what is meant by Maxwell inductance bridge, and we will study the circuit diagram for the Maxwell inductance bridge and for the phasor diagram and the balance equation for the Maxwell inductance bridge. In the Maxwell inductance bridge, I have told you earlier that Maxwell inductance bridge is a type of AC bridge which is used to measure the inductance by comparing with the standard inductance. Now in the Maxwell inductance bridge, it consists of four arms. In each arm there is three non-impedance, and one impedance is unknown to us. Then we have to find this one impedance. Now in this case, in the Maxwell inductance bridge, it consists of a detector. The detector, we have to check the balance condition for the Maxwell inductance bridge, and the Maxwell inductance bridge consists of AC supply power. Now let us look into the diagram. Now let us look in the diagram of Maxwell inductance bridge. Now this is unknown resistance in the unknown inductance, and this AC power supply, and let us this is resistance 3, so resistance 4. In the between there's a detector. That means I've already told you detector means it is used to balance the network. Now if this network is balanced, then there is no current will flow in this detector. That means the bridge is said to be balanced. Now in each arm there is a voltage. Let us consider E1, E3, E2 and E4. Now in this Maxwell inductance bridge, you can in the Maxwell inductance bridge you can see the impedance in the form of resistance and inductance, and in the arm AB you can see that there is the resistance and inductance are connected in series connection, and this R2, this is non-standard, and three non-impedance, and this arm AB is unknown to us. We have to find the unknown resistance and inductance with respect to all the non-impedance. Let us see what's the connection between the resistance and inductance in each arm. Now arm AB, and you can see in the arm AB that the resistance unknown resistance is connected series with the unknown resistance. Unknown resistance is connected series with unknown inductance. Arm E to B. Now let us see arm AB. Arm B to C. Sorry. In arm B to C, you can see that there is no inductance. That means it is non-inductor resistance. The non-inductor resistance means it is a pure resistive because it does not contain any inductance. Non-inductor resistance, that means it is purely resistive. really resistive. Now let us see in arm AB, C to D, sorry, C to B. Since it is similar case like B to C, there is no inductance. It is non-inductance, resistance, inductance, resistance. Now in A to B. Now A to D. Since the non-resistance is connected series with standard inductance, but I forgot to mention in this case, this variable standard inductance have internal resistance called R2. That means non-resistance is connected. Non-resistance and internal resistance. Internal resistance is connected series with standard inductance. Inductance means that is this is L2 and this R2. Now in this diagram you can see that in each arm there is a voltage drop across the arm AB, B to C, C to D, and D to A. Now let us see the balance equation for the Maxwell inductance bridge. Balance equation. Now you have to know that any type of AC bridge, the balance equation for any AC type bridge is given by Z1, Z4 equals to Z2 and Z3. Now this is the impedance. We have to find the individual impedance for the given arm. Now let us this Z1 is the impedance for the arm AB. Now in the arm AB you can see that the unknown resistance is connected series with the unknown inductance. That means Z1 is Rx, and the impedance for the unknown inductance is given by j omega Lx. And Z2, in the Z2 you can see that resistance 2 and internal resistance 2 and then on standard inductance. That means R2 plus internal resistance 2 plus j omega L2. Now impedance 3, the Z3 is the impedance for the arm B to C. That means it is a pure resistive. That means we have to write R3. And then Z4 impedance for the arm C to D is given by R4. Now we have to substitute all the impedance of the given arm in this balance equation. Now we have Rx plus j omega Lx. Now R4 equal to R2 plus internal resistance 2 plus j omega L2 times Z3. Now we have to cross multiply Rx R4 plus j omega Lx 4, and we have to cross multiply with R3 plus R3 plus j omega L2 R3. Now Rx R4 plus j omega Lx R4. Since R3 is common, we have to take it in common, and R2 plus j R2. Now in this case in each terms if there is no j omega, that means we have to consider is an imaginary real part, and any term which consists of j omega is imaginary part. So we have to equate the real terms separately and imaginary part separately. Now the real part for this is the real part, this is the imaginary part. we have to equate the real part to real part and imaginary part to imaginary part. For this, real part is R4 and R3, R2 plus the resistance. So since we are finding the unknown resistance, the unknown resistance is given by R3 equal to R4, R2 per R2, small R2. Now we have to equate the imaginary part to imaginary part. Imaginary for this is j omega Lx R4 now is given by j omega L2 R3. Since j omega get cancelled and Lx is L2 R3 is called R4. Therefore, from this we conclude that the unknown inductance can be measured by comparing with standard inductance which is L2. Now
Let us see the phasor diagram.
Then what's mean by phasor diagram is the phasor diagram. This phasor diagram shows the relationship between the various phasor. Now phasor diagram, it shows the relationship between the various phasor. The various phasor, as you can see in this diagram, since this AC bridge, since Maxwell induction bridge is connected to the AC power, we definitely know that there will be current and a voltage. And the current flowing to the each arm is generated by I1, I2, I3 and I4. And since there is also voltage drop across the arm AB and B to C, B, C to D and D to A, we have to draw a phasor diagram for the current and the voltage. So now in order to draw a phasor diagram, first we have to know that the relationship between the voltage and the current in terms of resistance, inductance and capacitance. For the resistance, we know that the voltage and the current is phase with each other, and for the inductance, the voltage and current is voltage will lead the current by 90 degree. That means current will lead the voltage by 90 degree for inductance. And for the capacitance, the voltage will lead the current by 90 degree. So to draw a phasor diagram, we have to take a reference point. Since in arm AB, when the current I1 is flowing across this arm AB, so let us take this I1 as a reference phasor. So reference phasor. In order to draw the phasor diagram for any kind of AC bridge, we have to take any phasor as a reference point, and other phasor we will draw with respect to the reference phasor. Now we have kept the I1 as a reference phasor. Now you have to see in this each arm. Since I1, we have to draw the phasor diagram for the current I1 and E1, and we have to draw the phasor diagram for the I1 and the voltage drop across each component of this arm for the Maxwell inductance bridge. Now since current I1 is flowing across this resistance inductance, first we will see the voltage drop across this unknown resistance.
So voltage drop across Rx is given by Rx I1. So since in the resistant part we already know in the resistant parts the voltage and current will phase with each other. That means yes I write I1 and I1 Rx. Since because they are phased with each other, voltage drop across the unknown resistance is phased with I1. Now for the inductance, also current I1 is flowing across the inductance part. So voltage across the inductance is given by J omega Lx I1. That means for the inductance parts, the relationship between the voltage and current is given by voltage will lead the current by 90 degree. That means the inductance in the inductance part of voltage drop will be lead the I1 by 90 degree. That means this will omega Lx I1. That is we have draw the relationship between the arm AB. Now we know that the voltage drop across the arm AB is the summation of the voltage drop across the resistance and inductance. So we have to draw a vector sum for the voltage drop across the resistance and the inductance, that is A1. Now let us move into the arm AB. Since arm AB, the current I2 is flowing across the R2 and small resistance I2, the R2 and inductance part, standard inductance part. So we have to also draw the phasor diagram for the phasor diagram for this. Now we see that E2 is given by R2 I2 plus R2 I2 plus omega L2 I2. Now we have seen that the voltage drop across arm ED is given by R2 I2 plus R2 I2 plus omega L2 I2. Now we know that the bridge is said to be balanced if no current is flowing to that detector. That means E1 will be equal, the voltage drop across the arm EB will equal to the voltage drop across between the arm E to T. So in similar case, the voltage drop across the arm BC means E3 is given by E4. Now we can see in this case that in the resistant part, since I2 is flowing across the R2, this is a resistive part. Since E1 and E2 is equal with each other, so any resistance part for the E1 must be equal to the any resistance for resistant part of E2, and inductance, this is inductance part, we have to equal it with the inductance for the E1. That means this will be E2. That means for this I2 R2 plus R2. Now since I2 and voltage drop across the R2 and small r2 is phased with each other, on the same line we have to write the I2. Okay, because the voltage drop across the standard inductance leading the I2 by 90 degree. So that's why we have to write in a similar case the voltage drop across the R resistance is phased with the I2. That's why we are showing the directions for the I2 as a reference phasors. Now that much is completed. Now in this similar case, now we have to look into the E3 and E4. Now now in similar case, when the bridge is balanced, the no current will flow in the detector. That means I1 will be equal to I3 and I2 will be equal to I4. That means if the I1 is equal to I3, so on the same line we have to write, since I1 is equal to I3, we have to I3. Since I2 is equal to I4, I4. Now now in the bridges, we also see the voltage drop across the R3 and R4. The voltage, this current I3 and this current I4. So when the current is flowing across R3, the voltage drop across R3 is given by R3 I3. The voltage drop across R4 is given by R4 I4. Since I3 and the voltage drop across R3 is phase with each other, in similar case for any resistance part, any voltage drop will be phased with the current. Now, if you show the phasor diagram for this, I4 R4. Now we know that I3 is equal to I4. That means this voltage drop across R3 and this E4 is a voltage drop across the R4. That means I3 is equal R3 and I4 is equal R4. Now since the voltage drop across the arm BC is equal to the voltage drop across the CD, that means we have to write this as I3 R3. Now in similar case, you can see in this phasor diagram that voltage since we are keeping the I3 as a reference point, because as I told earlier that when the bridge is balanced, no current will flow in this detector. No current will flow in detector. That means the current I will be equal to I3. In similar as on the same line, when I1 is equal to I3, so we have to write this voltage drop across R3 as R3 plus I3. So they are phased with each other. We have fulfilled the condition for the relationship between the voltage and current in resistance part. So this is the overall this is a complete phasor diagram for the Maxwell inductance. Here you can see that E1, we have shown that E1 is equal to E2, and for this we have shown that E3 is equal E4. So now overall AC power is given by E is equal to E1 plus E3, and to calculate the overall AC power for the Maxwell inductance bridge is given by E1 plus E3 and E2 plus E4. And if we draw a line, from this, we have to connect in this. So we will extend the resultant line and giving E is equal to E1 plus E3 equal to E2 plus E2. This is a complete phasor diagram for the Maxwell inductance bridge, and I hope you understand this concept, and thank you for watching.
Thank you for watching, and like and share with your friends.